Hello and welcome to today's webinar. OpenSim is a platform for improving quantitative ergonomic assessments. On behalf of the NIOSH-supported education and research centers throughout the country, we are pleased to present this 2009 Ergonomics webinar series, offering free monthly webinars on various topics on human factors and ergonomics. This collaborative effort on behalf of each ERC's continuing education program aspires to provide current research supported through NIOSH ERC programs. Thank you for joining us today. Today's webinar is brought to you by the University of Utah, Rocky Mountain Center for Occupational and Environmental Health, Andrew Merryweather, PhD, and Jonathan Mortensen, PhD. A few housekeeping items first. You will be muted during this presentation. If you would like to ask a question, please enter it into the online chat or Q&A. We'll save time at the end of the presentation to address questions. This webinar will be recorded and archived for viewing on COEH Northern California's website, Facebook, and YouTube channel. At this time, I'm pleased to welcome our presenters. Andrew Merryweather, PhD, is Director of the Ergonomics and Safety Program at the University of Utah and Associate Professor in the Department of Mechanical Engineering. He is also an Adjunct Associate Professor in the Departments of Family and Preventative Medicine and Physical Therapy and Athletic Training. He teaches and directs research in the areas of biomechanics, human factors, musculoskeletal injury prevention, and human systems modeling. Dr. Merryweather attained his PhD degree in mechanical engineering at the University of Utah in 2008 as a NIOSH trainee in occupational injury prevention. A significant amount of his current research is related to wearable technology to determine occupational exposures and safe human-robot interactions. Jonathan Mortensen, PhD, is currently an exponent associate in the biomechanics practice. John recently received his PhD from the University of Utah Department of Mechanical Engineering. Dr. Merryweather was John's academic advisor in the Ergonomics and Safety Lab. During his time at the University of Utah, John was a NIOSH trainee at the Rocky Mountain Center for Occupational and Environmental Health. He has investigated the various effects, including active neck muscles, on head injury metrics in various activities involving blunt force trauma, including American football. He has also conducted studies on ergonomic risk, sports performance, and muscle control. Dr. Mortensen has developed and maintains an OpenSim model on the head and neck, which is freely available through simtk.org. Thank you both so much for joining us.
Well, thank you.
Thank you. Glad to be here.
Yep. Good afternoon, everyone. We want to express our enthusiasm for the opportunity we have to speak in today's webinar and hope that you all find the information that we've prepared informative and thought-provoking, especially about how to improve the current status quo for quantitative ergonomic assessments using computational models and simulations. As was mentioned, I direct the Ergonomics and Safety Program at the Rocky Mountain Center for Occupational and Environmental Health here in Salt Lake City, Utah, as one of the 18 national centers supported by NIOSH. And our mission is dedicated to protecting workers and their environment through interdisciplinary education, research, and service. Benjamin Franklin is reported to have said that an ounce of prevention is worth a pound of cure. This was actually said to the people of Philadelphia in a speech about fire safety and prevention, but it's been widely used to motivate workplace interventions in occupational safety and health. So a question I have for us all is, how do we prevent something if we don't know exactly how or when it will occur? Our work's motivated by the magnitude of the problems surrounding workplace musculoskeletal disorders. As we know, about a third of all injury and illness cases are related to MSDs, and this results in lots of lost time, lost productivity and wages, and is a very high financial burden on our society. Ergonomics is concerned with understanding interactions among humans and other elements of a system with the goal of optimizing human well-being and overall system performance. We're currently experiencing another industrial revolution in a sense, where technology, cyber-physical systems, robotics, and artificial intelligence are really changing the way people interact and work in systems. As ergonomists, we need to understand how to optimize human well-being in this changing environment in what's been called Industry 4.0. This is going to be especially important if we're planning to prevent the future musculoskeletal diseases and disorders that we'll see because of this changing workplace. So over the next 45 minutes or so, we'll review at a very high level some of the driving factors that influence the development of musculoskeletal disorders. I'll present the case that methods being used to model risk are primitive and can benefit from improving our exposure assessment methods using computational models, specifically in this talk discussing OpenSim as a platform to understand and improve MSDs and their prevention. We've prepared a demonstration of a newly released model for lifting, and Dr. Mortensen's going to do that in just a few moments. That will discuss how back analyses and other methods can be applied to OpenSim to understand and enhance our capabilities in preventing injuries. So first, injuries to the musculoskeletal system can be grouped kind of into two large categories: external and internal or intrinsic factors that influence the development of these injuries or disorders, such as sudden external forces in concussions in American football, or volitional forces leading to low back pain. As we know, it's much more difficult to quantify the events or the elements that led to an injury if volitional force and chronic exposure is the cause. One of my colleagues at Sharp in Washington State, Stephen Bao, proposed a simple model, I put that in quotes, about how workplace organizational factors contribute to work-related musculoskeletal disorders. This model illustrates the complex interactions that exist between risk factors that are biomechanical in nature, psychosocial in nature, and all of these large risk factors contribute to the development of work-related musculoskeletal disorders. I think by now we recognize that MSDs are a complex multifactorial in nature, and these factors appear sometimes unrelated to just simple biomechanics alone because of those interactions. About a decade ago, Kumar proposed an injury precipitation model illustrated here, where constant work requirements and changing work tolerance capacity of workers over time can result in an injury. But what we know is that work is not constant. The nature of work is variable. In fact, it's becoming even more variable. So how do we adjust our models in our interpretation of work tolerance capacity to prevent these injuries from occurring when there's a mismatch between the worker's capability and what's expected of him or her on the job? One of the problems comes with the question, how do we measure physical exposure? Oftentimes that's through observations and interviews, sampling, video analyses, and more recently we're seeing more wearable sensors that have been miniaturized and are non-invasive for workers to monitor their activities on the job site. But another question is, how do we measure tolerance? Epidemiology, genetics, other models, simulations. How is it that we can understand when these events occur to prevent them, or how they occur? The goal of ergonomics is really to minimize this mismatch that occurs between human capabilities and task requirements. But what is the optimal scenario? If we look at these pictures where blue represents human capabilities and gray is the job demands, ideally we're moving towards a situation where human capabilities far exceed what's required of them on the job. So our objectives with ergonomics is to maximize efficiency of the human and the system that they work in, control the risk to both the human operator and the overall system, retain workers, which ends up being a difficult problem, and ultimately work towards fitting jobs to workers in an ideal sense where we can maximize the overall productivity and everything else of the system. So we're faced with some major challenges, though, with this goal in mind. Exposure measurement is difficult. Exposure monitoring right now relies largely on self-reports and observational methods, and there are very few direct methods used in our occupational assessments for doing this. Furthermore, our understanding of the exposure-response relationship is limited because of our ability to measure exposure to workplace risk factors. Our knowledge of how to prevent and treat musculoskeletal disorders is evolving and changing with more science. And our ability to predict injuries in order to prevent them is largely dependent on our understanding of this mismatch or fit between the worker and the environment or the system. Another issue with many of the metrics that are used currently in terms of task and job design is that they rely heavily on semi-qualitative or semi-quantitative or qualitative metrics that inform someone as an analyst to investigate it further. And what really does that mean? But why do we have incomplete exposure measurements? There are many reasons. Particularly, it's difficult to measure applied force. There are complex interactions, as we mentioned in that simple model proposed by Dr. Bao. We have few longitudinal studies that specifically in terms of their exposure monitoring are more than multiple snapshots in time of the exposure. They're by no means a continuous measurement of exposure over the length of these longitudinal studies, which in some cases limits our understanding of what's truly driving risk and resulting in MSDs. So an example here, we use generalized risk or risk priority scores to affect change and to investigate jobs for making these changes. But I want to suggest that these generalized risk and priority scores don't really equal true exposure. They're some surrogate measure of exposure, but they're not the actual exposure that we're trying to reduce or eliminate. So typical exposure measurements, as I mentioned before, self-reports, they're commonly used because they're inexpensive and relatively fast and easy, but they have their limitations with inaccuracies and subjectivity. The visual surveillance methods are more common, and they provide more quantitative results to the analysis, but they're still influenced a lot of times by subjectivity and maybe inaccurate because the exposure information that informs them is so limited and crude. Direct measurement techniques are oftentimes reserved for laboratory studies because they're not practical in the field. We're seeing a slight change in that with miniaturized and wearable sensors, but we're still not quite there yet where we can deploy sensors on workers and rely on that information. So of the visual surveillance methods that most of us in this webinar are likely familiar with, think about each of the factors that go into the scores that result from these analyses. And I want you to consider the fact that where do we account for differences in things like gender or strength or age or pre-existing conditions or prior exposures that change the susceptibility of an individual to that exposure that results in an injury? These models don't directly recognize any of these factors and many others that we know are associated with musculoskeletal disorders. So we think about personal exposure dosimetry. When I think of this, I go to my industrial hygiene colleagues because they have examples of dosimeters, such as noise or particulates and gases, and they're effective at measuring over time individual exposures. There are also permissible limits and threshold limit values that are adhered to for protecting workers based on these exposure monitors, these dosimeters. The real purpose of a dosimeter is to measure and analyze exposure for a period of time and then determine whether or not that exposure requires some form of action or intervention, or if it's considered safe. Due to the nature of musculoskeletal disorders, there are still many questions about the dose-response relationship between exposure to various types of physical hazards, let alone the numerous other work organizational and psychosocial stressors that exist that interact with the physical exposures to result in MSDs. We believe that an important step towards furthering our understanding about how to prevent these MSDs is, number one, improving our understanding of workplace exposures by developing some form of dosimeter for musculoskeletal injuries that can be used similar to the dosimetry that we see in other disciplines. One aspect of this work is exploring wearable sensors, as I mentioned. A former postdoc, Dr. Mitya Trokov, who was a postdoctoral trainee in our laboratory, has been pioneering some use of wearable insoles that are instrumented and algorithms to quantify material handling activities. And through this, providing real-time feedback or coaching to a worker to notify of hazardous motions, of exposures that are exceeding limits that have been preset or predetermined. But we still have a long way to go before these new instruments are reliable and valid as dosimeters. What I emphasize here, though, is that in order for us to use all of the data that are becoming available because of technology in a more efficient and meaningful way, we need better models. We need models to help us understand what happens when change occurs and how is the response going to be anticipated, and is there a clear cause and effect relationship that we can avoid if we do something at the job that otherwise may be unpredictable. I want to spend the rest of our time introducing an open source musculoskeletal modeling software called OpenSim. I hope some of you have heard of this. Maybe some of you are using this model and this tool. OpenSim enables the advancement of movement science by equipping research and clinical communities with both biomechanical models and simulation tools in an open source, extensible, and collaborative platform. Users can build, manipulate, and interrogate biomechanical models. They can be used to simulate musculoskeletal dynamics and neuromuscular control. And it really enables researchers with the ability to pursue studies that are otherwise difficult, if not impossible, to perform experimentally, and use these models to predict novel movements and adaptations to new workplaces, new environments, new assistive devices, including interacting with exoskeletons and other forms of robotics. There are certain benefits to using models and simulations for research, and especially for promoting efforts to move research to practice. First, models allow us to visualize human movement and study complex interactions. Second, these models using a validated model, we can probe various aspects of the musculoskeletal system, such as intervertebral disc pressures that are difficult, if not impossible, or too invasive to do in practice. Third, by performing simulations using models, we can perform various what-if analyses to inform how changes in our population, including strength or age or fatigue or prior injury, might affect the interaction that occurs between a user and the work environment. And finally, this can also be used as a tool to help identify cause and effect relationships if we make changes to the workplace or to the approach to work, the way that the work is done, organizational factors. Can we understand how those changes are affecting the musculoskeletal system? OpenSim contains a repository of many, many models. There are a few examples here that are freely available for conducting a wide range of human and animal studies. movement arises primarily because of a complex orchestration of the neural, musculoskeletal, and sensory systems. And OpenSim includes computational models of all of these systems, enabling the prediction and the analysis of the movement. OpenSim's underlying SimBody engine for multi-body dynamics also includes contact models and several solvers and integrators that allow users to generate muscle-driven simulations, or to even solve the muscle forces and moments that generate an observed motion using inverse simulations. An OpenSim model is really it's a codified description of a physical system and its dynamics, and often is expressed in this topological graph of interconnected components, such as bodies and joints and muscles and constraints. There are two primary parts of the model. One is a system of equations that includes all the physical parameters that are constant during a simulation, such as mass and dimensions or muscle properties, but also the states of the model that include a list of things that change over time, such as joint angles. Then the system automatically constructs the computational set of differential and algebraic equations to solve this problem using the dynamics of the model. OpenSim includes models of muscles, biological joints, and other musculoskeletal structures that are based on decades of research. And each of these models that's available for use has validation that's published, and the data are freely available so others can perform independent testing and validation, which creates this community of users where members of OpenSim can help validate these models and simulations by performing things like sensitivity studies and developing benchmarks for multi-body system analyses, or even analyzing parameter uncertainties in the model. OpenSim's novel component design provides access to all the underlying dynamic equations, along with quantities like contact forces and metabolic costs, which allows us to extend OpenSim and create custom solvers. For example, methods have been applied to predict movements like walking and jumping that optimize the user's determined objective, or optimizes a user determined objective, such as minimizing metabolic cost or maximizing jump height. Imagine if we could use these same methods that are largely not being used right now by ergonomists to understand how to fit people better into jobs, or how to fit jobs to people, and optimize things like reduced metabolic cost, or reduced muscle forces or joint contact forces. So as I mentioned, OpenSim and ergonomics, it certainly has the power and the capability to do a lot of the things that currently in ergonomics we're using more primitive methods to do, that rely a lot on hand calculations, for example, or simple spreadsheets. But I want to talk to you today about how ergonomics and OpenSim can be part of our future. And I'll introduce a model that was recently released and published called the Lifting Full Body Model. It's a model specifically designed, as you can imagine, for lifting. And it includes 238 musculotendon actuators. It's been validated right now for 8 material handling tasks, and the validation comes in the form of electromyography, intra-abdominal pressure measurements using capsules, in vivo vertebral loading using instrumented vertebral bodies, and also compared to the static strength prediction program from University of Michigan to look at compressive forces at the L5S1. It's considered a valid lumbar loading in both symmetric and asymmetric lifting, and some of the key advantages of this particular model over other models is that it incorporates all the dynamic properties of a lift. So I've asked Dr. Mortensen to provide us with a demonstration using this model to show how really quite easy it is to use OpenSim, and from using OpenSim, all the wealth of knowledge and information that can be gained without running a single physical experiment. So take it away, John.
All right, hopefully everybody can hear me. Someone will stop me if you can't. But my name is John Mortensen, and I'm very glad to be presenting to you today. Hopefully you've been enjoying and learning a lot from Dr. Merryweather's presentation. As he said, I will be just doing a live demonstration of OpenSim model. So as Dr. Merryweather was describing, we have a OpenSim model, a full body model, and this one is designed to look primarily at loads in the lumbar spine. Each of these red lines here is a muscle element, and muscles aren't included for the rest of the body because we're interested only in the forces that are occurring in the lumbar spine. So there are several steps you need to take in order to get useful information out of this OpenSim model, or able to get those compressive forces in the lumbar spine from this model. The first step of using any OpenSim model is to scale your model to be consistent with the subjects you're looking at. So this is a generic model, and it's been scaled to be consistent with a 50th percentile male, but if you're not looking at a 50th percentile male, you need to change this model to better represent your population. Now, OpenSim has a variety of tools. One of them is a scale model tool, which allows you to very easily change the anthropometrics of this model. So you can change the mass and size of this model to represent your subject. Now, you can go a lot more in depth than that. There are several research groups out there that are using MRI data to make these models extremely subject specific, where they'll change the size and shape of the bones and change where the muscles insert into these bones, and also change individual muscle strengths, all based on this MRI data. So there's a large range of what you can do with making your model subject specific, and I just want to highlight how that's true of most everything you do in OpenSim, that there are very wide range. You can do very broad, where you don't do much subject specifics, or you can go to very detailed and make your model very complicated, all based on the answer you're trying to get at. So once you have a scaled model, and for today we're just going to leave it as the 50th percentile male, the next step is to get a motion into your model. You can see here that you can play with the different joint angles in the model. You can make it move using these sliders. That's not going to be very helpful for looking at a dynamic task. The way you can get this model to move as you observe in real world, there are three real ways. The first is to use motion capture, and that is what is most commonly used, which allows us to do inverse kinematics. That's another tool included with OpenSim it does an analysis that makes this model move in such a way that it best represents what we captured through motion capture, and that's the traditional way of getting motion into OpenSim. Another way, in which you may be interested in, is you can do this through the use of IMU sensors. OpenSim has released a beta version of this, which allows you to put IMU sensors incorporated into this model to predict motion of the model. And the third way is to manually generate the motion. You can do it the way I've done for today, where you just specify these joint angles with time in a file, or you could do something more complicated, as Dr. Merryweather mentioned, that there's some pretty impressive research out there that is driving motion through optimization techniques. And OpenSim will be releasing tools to do that in 2020, so that's exciting. But for today, I'm going to load a motion that I just created, as I discussed, of a simple lifting task. So you can see it starts bent over, and it stands up and bends the arm throughout the task. So there's nothing too fancy going on here, but now we have motion included in the model. Now, OpenSim will give you access to anything you want that goes into this motion. So you could look at joint velocities, joint angles. You could look at accelerations of different points on this model. We can get a lot of different kinematic data, which is all very interesting. But as ergonomists, we're going to be more interested in the forces that are involved. So we can predict, what the force moment generations are at individual joints, but if we're going to drive this model using these muscles, we need to have a way that predicts how much force is in each individual muscle fiber. OpenSim has two tools to do that. First is static optimization. The second is computed muscle control. Static optimization is a little bit more user-friendly, but provides a little bit fewer results that you could play with. So this is the static optimization tool. I'm going to input some predetermined settings that I've already set up. We can hit run here and watch this model move through this motion as driven by the muscles themselves. So you can see in the simulation as muscles turn red, they're becoming more active. And when they're blue, they are 0% active, all the way up to all the way red is 100% active. So you don't see a lot of muscle activity occurring in this static optimization. And you can see, as you would expect, muscle activity reduces as the model becomes more erect, as there's less moment requirement. And so we can look at this motion again, that the muscle fibers change from red to blue, less activation. So what you can get out from here is you can get individual muscle activation, individual muscle forces, which could allow you to predict things such as fatigue, which muscles are going to get fatigued soonest by doing this sort of motion. You could also use this to develop metabolic analysis, that you could understand how much of a metabolic demand there is from this motion based on which muscles are active. Now, in order to get joint reactions, we'll use one more tool, the analyze tool, which will use outputs from the static optimization tool to develop these joint reaction forces that we're interested in. So again, I have a set of preloaded options set here that we can run. This one runs much faster because there is no optimization occurring. It is just running through a set of equations. And then finally, we can plot this. And when I specified the options for the Analyze tool, I made sure that we were looking at the joint loading of the L5S1 joint, and I did it in the reference frame of that joint. So that will mean that this force in the Y direction will give us the compressive loading at the L5S1 joint. And so we can see that it decreases, and it's only at 1,300 newtons, which is not a very dangerous lift. And that's because we don't have any loads in the hands yet. This is essentially just the model doing a squat. And we can add load to the hands by using a force file that we can specify in static optimization that you can do some very fancy things with. You could do forces in different directions, and you could change the magnitude of the force over time. You can add torques, and you can apply force to any body in this model. Or we can do it a little bit simpler, and we'll do that for today's demonstration, that we will just change the mass of the hands. So you can see that the mass of the hand, each hand is about half a kilogram. If we increase that to be 10 kilograms for each hand, so we're getting close to a 20 kilogram lift here, a little bit less because we're including the mass of the hands already, and we can run this task again and see how the muscle activation and also the joint loading changes as a result. So you can see already, as it's doing the first step of this optimization, that there's a lot more muscle activation required. More of the muscle fibers are required to make this motion possible, as well as they are active to a higher degree, which would indicate that there's a lot more force required, and as we'll see, more compressive loading. And again, you can get a lot of amazing, a lot of information out of this model. That you could get muscle forces. If you use the computed muscle control algorithm instead of the static optimization tool, you could get things like passive forces versus active forces of the muscle, tendon length, fiber velocity, and a lot of things that we could use for generating these predictive models. We'll run this analyze tool one more time. and then we can add this data to the plot. Again, we're looking just at the compressive loading in the spine, and we added 20 kilograms. Now we're getting up to more like 4,000 newtons, which is beginning to be a little bit more dangerous of a lift. And so what I've shown here is that you can change a parameter in the model and see an output that you would expect. So you can start to do these what-if studies. Now, one of the really powerful things about OpenSim, apart from being able to go from not very complex to very complex, depending on your needs, is that you can run OpenSim out of a MATLAB or Python scripting environment. And so that means that you can run these same simulations and collect data iteratively, all with setting up a loop inside of MATLAB. So you can imagine that you change different parameters in the model, whether it be the weight of the hands or how the load is applied to the hands, the way the lift is done, changing the posture, the speed of the lift. You could change individual muscle properties to make this model be stronger or weaker or show disease. And you can have them all run and do these what-if studies pretty easily from OpenSim. And if any of you are interested in these very simple examples that I provided here and want to use for showing some of the abilities of OpenSim, feel free to contact me and I can send these files to you. They're very simple to run and might start as a good introduction to OpenSim. But now I will ask Andrew to take control of the webinar again, and I'll stick around for any questions that you have at the end.
All right, thank you, John. So you're probably already scared of OpenSim by now after that demonstration because of all the features and complexity, I guess, of the model. But I hope I can alleviate some of that fear in the next 10 minutes or so, talking to you about some additional work that we're doing here in Utah. And I'll start with the rapid upper limb assessment, RULA. One of the most widely used methods for assessing upper extremity ergonomics, postural based. And from these postures, we derive a risk score like we talked about before. One of the challenges, however, using this method such as RULA to really understand the cause of upper extremity MSDs is the lack of many other factors associated with risk that arise from the dynamic nature of the movement. Also, there are very coarse posture categories, and the risk scores aren't very specific. So we're using OpenSim right now to augment the risk scores that people are familiar with using RULA to add additional details that can be assigned with a more comprehensive approach. And for example, something simply that's neglected by RULA, in fact, every model and assessment technique that I talked about before, is something like the direction of the load on the hands. If you're pushing or pulling, or if you're twisting, none of those changes to the response are evident by the model results in the score using traditional methods, but they are in OpenSim. So we conducted a study to evaluate correlations between RULA and OpenSim, and what was found is the contact loading in the joints was most associated with the risk scores that are defined by RULA. So with further work, our plans are to expand this in order to understand specifically what factors are related to MSDs like carpal tunnel and medial and lateral epicondylalgia based on the response to the musculoskeletal system that's driven by the original exposure. The HYOID model that John mentioned is something that was the foundation of his doctoral work, and it's a head and neck model to produce realistic strength in all the principal directions of the neck. And we've used that for things like fall studies, adaptive technologies in sports with spinal cord injury patients, American football and concussion risk, and whole body vibration with commercial drivers. So we know that there's a high prevalence of neck and back pain and shoulder pain among commercial drivers. And the whole body vibrations interacting with and changing cardiovascular function and respiratory response, and also changes to the skeletal system, including some evidence of increased bone mineral density with whole body vibration. But our question was, does posture modify the transmission of the whole body vibration? And if so, can changes in driver posture affect their musculoskeletal response? So the long-term goal was to understand the effects of driving time, posture, and whole body vibration on truck driver neck pain and neck fatigue. But our short-term goal in the study that I'll present here uses the HYOID model in OpenSim to help us define the relationship between posture, vibration, and the resulting muscle activation requirements to maintain that posture during driving. In order to do this, this is some of Dr. Mortensen's work. He simulated a combination of lower cervical spine postures, upper cervical spine posture, torso posture, and whole body vibration frequency and amplitudes. And this parametric study ran all the combinations of these postures and vibration frequency and amplitudes, and then produced a whole suite of data from OpenSim. What we found is that there was a statistically significant change in muscle response to amplitude and frequency of the vibration. Posture was a little complicated. So for example, if we look at the figure here, this is a neutral, upright, erect neck posture. If someone slouched a little bit forward or flexed their neck forward, that increased or decreased the muscle activation. But if you combine a neck flexion with a change in torso posture, essentially that postural component was negated. What we did find, however, was using these factors in this parametric study, we could predict with an R-square of 0.85 using amplitude, frequency, and posture what the muscle activation would be in the neck. We also found that poor posture may actually exacerbate the effects of the transmission of the vibration. So in this graph here, I'll use neutral and slouched posture as indicated by this picture. We see that the reason that most of us slouch when we're seated is because it requires less muscle activity. It's more comfortable because it doesn't require as much muscle activity as shown here. When we induce a vibration in those posture, first the neutral posture, we see the effects of that whole body vibration on the muscle response. But if we do the same thing with the same vibration input in the slouched posture, we see almost a doubling effect of the required muscle activation to maintain that posture. Now, this was just a parametric study. We have no experimental data. This is all simulation based. But fortunately, we've just been connected to Dr. Jay Kim at Oregon, who's done a host of experiments using a vibrating simulating platform with over 100 people with EMG and motion capture and a number of other things. And we're working with his group now to confirm these results and verify whether or not we see changes in EMG as our model suggests that we would, given changes in posture. Finally, fall injuries and flooring. We know falls are a big problem, especially in older adults. The severity of injury from falls correlated with stiffness of the floor. And so we wanted to experiment and see if we could reproduce data that are published in other papers looking at floor stiffness or compliance and impacts to the head. So we did this by reproducing in simulation the experiments that were run and published. And those two experiments were one dropping a head form as shown here onto a compliant surface, and the other was to investigate the effect of actively contracting the neck to prevent head impact during a backwards fall. So with OpenSim, we were able to reproduce these studies, and we quantified the risk of a head injury using the head injury criteria called HYOID, with the equation here that uses acceleration in time. And we also simulated a fall onto a compliant floor, so think of a softer floor versus a hard floor. And from this, we were able to confirm that using simulation, we closely matched the results that were published in the literature by these two other independent studies. We also found that only a small amount of activation in the neck makes a big difference in terms of the head injury criteria. We see a reduction of almost 36% in the impact force. We, of course, need more studies like all good research, but OpenSim can be used to rapidly study things like muscle fatigue or muscle weakness and reaction time and other fall types in scenarios that would otherwise take many, many months or years and lots of resources to do. So in summary today, I hope after seeing some of the things that OpenSim's capable of, I want to stress the fact that I think occupational safety and health professionals, specifically ergonomists, are underutilizing some of the advanced models and simulation methods that are being produced. And it's not because they're not available. These are open source, freely available models with an entire user community of support to help advance our understanding of musculoskeletal disorders and prevent them. The future development of these models, though, depends on us, because other scientists and researchers have their research questions. They're trying to understand, many things, not necessarily ergonomics. If we want these methods and models to be useful for ergonomics, we've got to do the work. The future will enable new sensors to measure our exposure, better models to predict and prevent injury, even novel applications of existing models to improve methods for job design and reduce musculoskeletal injuries. So in conclusion, I want to say the future depends on what we do today. And that's by Mahatma Gandhi. So thank you for your attention, and we'll turn the time back over to the moderators.
Wonderful. Thank you so much for your presentation. At this time, if you have any questions you would like to ask our presenters, you're welcome to enter it into the online chat box or Q&A box here. We have reserved some time for questions. I would actually like to get started by asking how widely utilized is OpenSim, and if you could provide any non-academic examples of organizations that might be taking advantage of this software.
So certainly, I'm not sure, John, if you want to take this or I will. This is published at Stanford's website. It's a worldwide group of users. There are users both, of course, in academia and research, and many other scientists and developers using OpenSim for things like robotics, rehabilitation, surgery outcomes. John, maybe you have more specific examples, but I want to just point the group to the sim.tk website where all the data for that question are available with even an infographic.
No, I think that's a good answer to look on SimTK's website, but for sure it is growing faster and faster. That is becoming much more widespread, and it's becoming more user-friendly as well. They've just released a updated version of OpenSim. They did that a few months ago. That is has a little bit easier interface for people that are just beginning with OpenSim to learn how to use the software.
Excellent, thank you. And yes, if you would like a copy of the presentation, we will have this online on our website, coeh.berkeley.edu. It'll also be available on our YouTube page for watching after the event. And we can make a PDF of the presentation available upon request. Another question here, how feasible would it be to bring this to the automotive manufacturing industry, especially in terms of collecting motion data with workers?
So that's a great question, and something that certainly the automotive industry partners are pioneering new technologies, including simulations in the earliest stages of the design. Right now, most of what's used are visual methods, whether it's through traditional cameras and image processing or more like marker-based motion capture. As John mentioned, though, OpenSim is now piloting a beta version of an IMU-driven OpenSim model. In other words, if you have IMUs on workers, those data can drive in real time or near real time OpenSim simulations that can be used not only in automotive, but just about anywhere you can use an IMU on a worker.
Thank you. Another question, for someone who has never used OpenSim before, would you recommend some good resources to kickstart? And what are some of the key skills to possess that will successfully allow operation of OpenSim?
All right, I can take this one.
Okay.
So OpenSim has like on their website, they have several tutorials that I would recommend going through all of them, because you start to learn just what OpenSim is capable of, and you start to get a feel for the system itself. And so the best place to look are the OpenSim tutorials themselves. Another great resource is that OpenSim has a very active forum that you post questions to, and people post questions all the time, and they're answered within a day that help you as you are struggling to get things to work inside OpenSim. So it's a very active community that if you reach out, people are willing to help. As far as key skills to possess to successfully use OpenSim, I think the useful thing is a good background in general biomechanics, but other than that, it's really just you need to take the time to learn the basics of OpenSim through the introduction. If you want to get more in-depth into what you can do with OpenSim, it's useful to have some skill in either MATLAB or Python so that you can run this OpenSim in more of a scripting environment. And if you really want to get in depth with OpenSim, it's possible to extend the features of OpenSim. They allow that through adding code through C++. So that's another thing you could do, but that requires a lot more background skills to be able to use. But to just get started, there's not a whole lot of additional skill you need other than just being able to run through the introduction. The examples, sorry.
And if you don't mind, if I jump in and just add, a lot of it really, it requires a desire to learn how to use the software. The software can be daunting if you get into it and you really aren't interested in harnessing some of the capabilities that are possible. It's just amazing to see what's possible through modeling and simulation with today's computational tools.
Great, thank you so much. We have another question. How does OpenSim compare to Anybody?
Well,
go
ahead.
So they're quite similar. I asked this question to some of the vendors of Anybody at a conference at one time. And they shed a little light on that, but you can go to Anybody to understand how they work a little bit better. But some of the differences are that OpenSim is free, Anybody is not. And Anybody does have some features one that I know off of the top of my head is it's better at predicting closed loop kinematics than OpenSim can't do that. So Anybody has some capabilities that OpenSim does not, and it also has some extra support you might get through paying for it. But other than that, since I'm not didn't use Anybody, you'd have to learn more about Anybody's capabilities directly from them.
Thank you, John. Did you have anything to add, Dr. Merryweather?
Well, not necessarily. Just to emphasize again that OpenSim is open source, so you get what you pay for. But with that in mind, I just came from the International Society of Biomechanics and American Society of Biomechanics joint conference in Calgary a couple of weeks ago, and I would dare guess over 90% of all the users of thousands were using OpenSim for things from spinal cord rehab to relatively simple biomechanics. Because it's open source, it enables people to use it. And I think you see a much larger user base because of that reason.
Great, thank you. Does the program work on Mac or on Windows or both?
Yes, so the answer to that question is both platforms as of recently. In the past, so as a year ago, it only worked on PC or in a virtual machine on a Mac, but now there's a native supported Mac version as well as PC.
Thank you. Have you done any trials with other ergonomic methods such as OCRA, NIOSH, REBA, etc.?
The answer to that question is bits and pieces, yes, but not explicitly like we did with the RULA. The model that John used for the lifting model did have validation for methods. 3D SSPP is a common one that's used, but not directly with the NIOSH RLE or the Washington State lifting models.
Wonderful, thank you. We do have a couple more moments. If there's any more questions, do feel free to enter it into the chat box and Q&A box here now. But I would like to again extend our thank you to both of you for coming in and sharing this information with us. We do these monthly ergonomics webinars in cooperation with our NIOSH Education and Research Center partners around the country. And so these are something that we would be happy to continue on doing as long as people keep showing up, we'll keep having it. Next month, we have coming up the fatigue failure approach for ergonomic assessment research updates. And that is with Sean Gallagher, PhD and CPE. That'll be on September 18th. All right, it looks like we have answered all of the questions that I see coming into the chat boxes here. So thank you all so much for your time today. I hope you all have a wonderful rest of the day. And if you have any other follow-up questions, please feel free to reach us at coehce@berkeley.edu. Make sure to check out our website, coeh.berkeley.edu. That is where you can find more news and information about our upcoming presentations and other free webinars. Thank you all so much, and I hope you have a good one.